All right, welcome. In this video, we're going to continue taking a look at dynamic programming. In the last 3 videos, we've looked at dynamic programming in one dimension, where the data structure that we use to store the subproblems is just an array, a one-dimensional array. And now we're going to shift into 2 dimensions, meaning we're going to use a 2-dimensional array now to store our subproblems, the solutions to our subproblems. And that means we might have a little bit more freedom in how we are going to, in the order in which we're going to solve our subproblems. All right, before we get into today's problem, let's just revisit the dynamic programming design technique that we presented in an earlier video. Again, we're hopefully getting fairly familiar here. The first step, state the problem as formally as possible. We'll get to that in a second. Then, because dynamic programming is like divide and conquer, our next 2 steps are again familiar. We're going to look for this relationship between the main problem and its subproblems. This relationship, remember, we call optimal substructure. If our problem has optimal substructure, then we can apply either divide and conquer or dynamic programming to that problem. Remember that divide and conquer will be top-down and recursive, and dynamic programming will be bottom-up and usually iterative. And since we're focusing on dynamic programming, step 4 becomes important here, which is identifying that our recursive solution, if we were going to apply our divide and conquer, that recursive solution has overlapping subproblems, meaning we solve the same subproblem more than once in that recursive tree. And that's going to be wasted work then, and wasted effort. And so we don't want to have that wasted effort. So that's our indication, hey, we should apply dynamic programming instead. And so that's step 4 is our pivot away from divide and conquer and into dynamic programming. And then the rest of dynamic programming, again, is fairly straightforward. If we apply the technique, we have to, first of all, decide on some kind of data structure to store the solution to our subproblems. Well, I just hinted at that. Today's video is probably going to involve 2-dimensional data structure. Okay, but in general, we could have any type of data structure, a 1-dimensional array, 2-dimensional array, n-dimensional array, or other data structures that might be useful if we have a problem that's a problem related to trees. Then the data structure we might have might be a tree structure. Or if the problem we're focusing on is a graph, then we might have a graph structure. And in fact, one important algorithm, actually there's a couple important algorithms on graphs that are dynamic programming on a graph structure. And the one I want to foreshadow a little bit is Dijkstra's algorithm for finding the shortest path between 2 nodes in a graph. Okay, that's a little foreshadowing, heads up. But the focus of this point was step 5, deciding on a data structure to store our solutions to subproblems. Okay, so we've decided on that. Now we just need to decide what order to fill that data structure in. When we had a 1-dimensional data structure, that was straightforward. We start at 1n, 0, 1 usually, and just go up to n where we were trying to get. That was the main problem. When we get into 2 dimensions, we'll see there's more than one way we can fill in that 2-dimensional structure, and so we sometimes have freedom to make that choice, and sometimes we don't. We have to do it one way, and that's the only way. But after we've decided how to fill that data structure up, then that will allow us to solve the main problem. Then we usually just finish off with a little analysis, make sure that we know what type of resources or how much resources are being used by our algorithm, specifically the time and the space. Okay, let's take a look at our problem here today. Now again, this is going to be another example of a toy problem. Here, a toy problem being a problem that I've just sort of made up for the purposes of studying something else, usually. In this case, it's studying dynamic programming. And this toy problem I actually designed after attending an ACM programming competition. And so I might just mention a little bit about what that is. The ACM is the Association for Computing Machinery. It's a sort of professional association for computer scientists, and every year they run a programming competition, an intercollegiate or an international collegiate programming competition, where college and university students from around the world participate in teams of 3 to solve as many problems as they can. And every year they have a set of problems, and occasionally when you go to a competition, there will be sort of a theme behind the problem. So one year that I went recently, every problem was a Star Trek themed problem. And so they had to do with phasers or Klingons or something else. And so here I've actually stolen one of those Star Trek problems, which was actually a problem about the Enterprise trying to escape a nebula full of Romulans. Well, I just changed it into, well, now you're a warrior trying to escape a dungeon full of goblins. Now the difference is I had to change that problem a little bit just to make it a little bit simpler. And remember, this is a toy problem. We're trying to just understand how two-dimensional dynamic programming is going to work, and we're not trying to make things too complicated on ourselves. So what I've done here to simplify things, I've made a few simplifying assumptions, and I'll maybe point them out as I go. Well, let's take a look at the problem as I've got it stated. So it says here, you're a brave warrior. You're trapped in the top left room, room 1-1, of an n by m maze. Here it looks like n and m are both 5 in my example maze down here. I guess I've got it stated here, it's a grid of rooms. Okay. The exit from the dungeon is in the bottom right. Okay. In every room there is some number of goblins that we're calling Gij, where Gij is greater than or equal to 0. And we can see that the little map I've got down below there indicates how many goblins there are in each room. You want to escape to meet the minimum number of goblins. So you're going to have to fight these goblins on your way out. You want to meet the minimum number on your way out to make it as easy as possible. To make things a little bit easier, here's where the simplifying assumptions come in. To make things a little bit easier, we're only going to move closer to our goal in each step, meaning we're either only going to move to the right or we're going to move down. We're not allowed to backtrack, basically. And the reason for that is, well, backtracking makes this a little bit harder. If we allow backtracking, we've changed this problem effectively into the shortest path problem in graphs, meaning we should use Dijkstra's algorithm to solve it, and that might be something we could return to after looking at a future video when we look at Dijkstra's algorithm. But for now, we're going to keep these simplifying assumptions in. We're only going to move right and we're only going to move down. No backtracking allowed. That makes it a little bit easier for us to solve the problem and find the optimal route out of the dungeon. All right, the first question posed for us here is, can we formalize this? Meaning, can we take this simple English description and turn it into a formal information processing problem where we have input and output? All right, so here I've maybe got us set up for potentially allowing us to come up with an input and output relationship. Now let's think for a second, what was the input? Now, there was a lot of information given to us in that paragraph. Some of the information is input. Other information is something that we just sort of assume to be true. Okay, so for instance, we are gonna, or the location of the exit in the bottom right, we're just sort of going to assume that that's going to be true. We're not going to have to add that as part of our input. Likewise, the fact that we start out in position 1-1, let's just assume that that's true. We don't have to put that as the input. We could imagine a more complicated problem where those were also part of the input. But if we need to solve that more complicated problem, well, solving this simpler version first would probably be a good first step. So let's only focus on that. Now, the one thing that did seem important is in our grid we had some of these numbers in here, right? These numbers, that looks like the actual input we were going to get. So let's start out there, and I'm going to give it a name. Let's see for a second here. I'm going to call it maybe G for goblin, right? And how many goblins there are, and maybe to make it kind of in the same form we've done before. We've been sort of stating this 1 to n as my indices here for that, but this is going to be a two-dimensional input now, and so maybe I'll go 1 to n, 1 to m. And this is just going to be the number of goblins in each room. Okay, so That's going to be our input. Let's maybe think to ourselves, is there going to be any other input we need? We mentioned maybe n and m, maybe 1 and 1, things like that could be input, but we're going to assume those are just assumed ahead of time. And maybe we're not done actually with the input. Maybe there's more, but there's nothing really, it doesn't really hurt to go on to the output, because sometimes when we start working on the output, we'll think, oh wait, I needed some extra thing in the input. I forgot about K or something else that was up here. But for the moment, I feel like that was probably our input, all the goblins. So what was the output? Now, remember, this problem, like some of the other ones we've been looking at so far, is an optimization problem. What does that mean? We're trying to do a min or a max, right? But it's a min in this case, right? Oh, we haven't stated I was trying to find. That's what we're trying to put here. One of the things we're trying to put here is a min. So since we were trying to find the min, usually we have some value related to that. Okay, and actually, I need to be careful. I was about to say, okay, let's call it m for min, right? Ah, damn, I already have an m written right there, so let's be careful. Maybe let's call it lowercase g. Uppercase g is my graph, my grid. Okay. So g is going to be the minimum number of goblins. Now remember, we also, when we're doing these optimization problems, the min or the max is not the only thing we usually want. Occasionally it is. Every once in a while, all we care about is what the value is. But usually it's more important when there's something else. We want to know how to get out of this grid to achieve that minimum number of goblins. So there's going to be a second component here. Okay, G is the minimum number of goblins, and now we have to talk about this path. What is this path going to be? Now this path, here's again where some simplifying assumptions going to come in. We've said that we're either going to move right or we're going to move down. So another way of saying that is every step we make will either be a right step or a down step. Okay, so the path leading out is going to be, here I'm going to start borrowing some mathematical terms. I'm going to say, and a sequence. Remember what a sequence was? We talked about that in our last video when we looked at the longest increasing sequence. A sequence is an ordered set. So here I'm going to say a sequence of what? Of these things. Rights and downs. Okay. Where this sequence of rights and downs is a path out of the dungeon. With G goblins, of course, where we want the path out of the dungeon to be the one that achieves our minimum, the G goblins. Now there's probably different ways we can say this. We could have come up with something different than right arrows and down arrows. We could have put zeros and ones here, or R's and D's, there's lots of different ways we can formalize this. But if this is the way to judge if this is formal enough, is this formal enough for us to go on to our next step and begin to design the algorithm for? Okay, let's maybe just see if we can compare that to what we have on the slides. We might have something slightly different here. All right, it looks like we have something pretty similar here. We have our G. We got the minimum number. Here I gave the sequence a name. I called it A. I guess that's useful if we want to start referring to it in some way. And again, here I maybe said the optimal path. It's slightly different wording, but we're dealing with goblins in a dungeon, so that this isn't something that's already been mathematically studied. And in fact, we probably could abstract away the fact that these are goblins or everything. We could call these numbers in a matrix if we wanted to. And if we call them numbers in a matrix, that's just a very abstract math problem that we might think, hey, that's not a really interesting problem, until we realize, hey, it corresponded to the goblin problem or some other problem that is a real world problem. All right, so one thing I wanted to do here is I want to think about other possibilities. Now, as we're getting into our design strategies here, we've talked about divide and conquer, we've taken a look at dynamic programming, but when we set up, we're starting to have a toolkit of different ways we could solve a problem, and I maybe just want to go through a couple now. The first way that I haven't really talked about a lot is called brute force. Now brute force is characterized, brute force, what does that mean? That just means throw all your computational power at it. Just do it all, just try everything, and that's really what we're here, try everything. What does that mean? Well, if you've got an optimization problem here where we're trying to minimize, then the brute force solution, try everything, says try every path. Try every path out, figure out which one is minimum. Our normal solution to the minimum algorithm, if you have the problem find the minimum element in a list, the algorithm you apply is a brute force algorithm because it says try every one. Look at every entry and see if it's the minimum. Okay, so sometimes that's the only way to do it, okay, is to try every one, or presumably, all right? But then we also said, well, what about divide and conquer? This is more clever than brute force. This is a different kind. Remember, this is recursive, top-down. In some cases, it might not be trying everything. A good example of that is binary search. Okay, binary search does not have to look at everyone because it's more clever than that. It can rule out a whole section of the list. Okay, that would be a divide and conquer. It's not doing brute force. Okay, and then we might say, okay, we've also got this dynamic programming. This is where we are now. And dynamic, again, slightly different, but not usually a brute force. But here we are sitting, and we're going to add a few more of these. We're going to add greedy on here as well. And greedy is another type of algorithm design. And there are probably a few more. Linear programming, a couple other down here that we might want to add as good algorithm design techniques. But when you start out with a problem like we've got here, Dungeon Escape, you might not know which of these tools to pull out of your toolkit. Should I grab my greedy and try a greedy algorithm? Should I jump on the divide and conquer dynamic? We know those ones are kind of siblings, so we try them at the same time. Or do I just go ahead and brute force? And that's sort of what I want to do right now. Let's say, hey, maybe I'm not feeling clever today. Can I just brute force this? And usually brute force is not a very clever algorithm in the sense that, hey, if you're not feeling very good, you could still sit down and write it. It's simple. It's try every one. The hardest thing is figuring out how do you try every one. And that's really what I want to think about right now. Okay, so here's just a simple little grid here. And remember, we made a couple rules here that we're only going to be moving right, or we're only going to be moving down as we move. What that means is, we'll notice, with a little bit of analysis, that every path is going to have to go 1, 2, 3 in this grid, right, and 1, 2, 3 down. Now here, if we're careful, we'll notice that this 3 I calculated out here is actually n minus 1, and that on the way down here is m minus 1. Okay, well, n or m depending on how we set up our dimensions, but rows and columns here we have n minus 1 and m minus 1. Okay, meaning the total path length, the length of the path is going to be n minus 1 plus m minus 1. n minus 1 rights plus m minus 1 downs, which the total number of steps is going to be n plus m minus 2 steps. Okay, now let's just look at it for this particular problem here. This one we could go right, 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 and then down, down, down. Okay, that would give us right, 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 down, down, down. That would lead us here. Okay. Now notice, if we take this string, I'm now treating this as a sequence, right? We call this a sequence of lefts and rights. I'm now treating this as a sequence. Now imagine shuffling it. Okay, you shuffle it. If you shuffle it in any way, that will just give you one of the different paths through this matrix, still obeying our rule, rights and downs only. Okay. For instance, we could put all the downs first. We could go down, 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 right, right, right. That would be a different path. Or we could go down, right, down, right, down, right. That would be a different path. Or right, down, right, down, right, down. Or right, right, down, down, right, down. There's a whole bunch of different ways that we can do this. Every one is going to be a string of length 6, and every one's going to have 3 down arrows in it. So here's a little bit of combinatorics for us. Hopefully we remember this. That the number of ways that we can distribute 3 down arrows in this list of 6 is 3 choose 6. We need to choose 6 of those locations to put down arrows in, and once we've done that, the right arrows are fixed. We have to put the right arrows in all the rest of them. Or, moving to our more general case, we're getting an n minus m, n plus m minus 2. All choose, now here 3, what was 3? 3 was how many downs we had, or how many rights we had. So n minus 1. This is actually going to be equal to n plus m minus 2. Choose m minus 1. Go ahead and verify that yourself if you like. Those are indeed equal. Okay, but this value, if we remember now, these choose values, these combinatoric values are coming out of Pascal's triangle, and in particular this is going to be Pascal's triangle on row 6, or this is going to be Pascal's triangle on row n plus m minus 2. And because these numbers here, especially when n equals m, this value is going to be one of those middle numbers in Pascal's triangle. Well, those middle numbers grow kind of exponentially. It's hard to rub. I'm kind of trying to wave my fingers at it a little bit there. They kind of grow exponentially because the sum of the whole row grows exponentially. But the middle ones are the ones that grow the fastest. So what the point is how many paths are there through this particular maze? A lot, an exponential amount. And do we want to do the brute force algorithm? Well, if there's that many paths we need to check, no thank you. Okay. Now, if we've ruled out that one, try everything, then the rest of them, oh no, we have to put on our clever hat. That's the next step. If we don't just try everything, then we have to be clever. That means, okay, we need to think up something more clever. Well, how could we be clever here? Well, one thing we might notice is that some of our paths share parts with other paths. So this, this path here, and if this path is good, if this is a good path, then all the good paths that might lead to the exit will probably have this part in it. So if we can find maybe good pieces of paths along the way, little paths along the way that were good, we could maybe build them, put them together to build one really good path on the way out, without having to maybe check bad paths. If we find this bad path over here, well, just never go down it. Maybe this path down here had too many goblins on it, so it turns out to be bad in the long run. We'll just never look down that path, or rather, we'll never end up going down that path. We are going to try to calculate as many paths through here as possible, but by not being so brute force and not being clever and just repeating, those calculations that we can see now, like, calculating 2 paths might have to recalculate that same sum over and over again. There's probably a clever way to get around that without having to recompute that sum. And that's where our dynamic programming is actually going to kick in. Right then, so to continue with dynamic programming, if our goal is to do dynamic programming, well, I guess it's dynamic programming or it's divide and conquer. Let's try and come up with a self-reduction. So to do that, I'm going to give myself a function to work with. I'm going to call it dungeon escape. Now remember, to do this, usually what we're going to have to do is we need to think about what kind of sub-problems we want to solve. All right, imagine we're trying to get down to this cell down here. We want to know what the minimum number of goblins it's going to take us to get there, right? Well, we're going to think to ourselves, well, what kind of sub-problems do we want to think about? Well, we probably want to know, if we knew what the minimum number of the minimum number of goblins it took to reach this cell, or the minimum number of goblins it took to reach that cell, since these are the only 2 cells we could come from, if we're going to arrive at our target cell, then we probably could figure out the minimum number of goblins to reach our target cell if we knew how many goblins it took to reach one of these 2 cells. So what does that mean? That means we probably want to know the minimum number of goblins to reach these cells, but to know this cell I'd need to know this one and this one. For this one, again, this one and this one, and so on. So I probably need to know the minimum number of goblins to reach any particular cell. Now if you'll notice, our cells, maybe we have an N by an M here, but we could use an I and a J to sort of index over them. This is an indicator that we have a 2-dimensional problem. Okay, in this problem we're thinking of both varying N and M, and because of that, since we might vary both of them, our decision is that this is probably going to be a 2-dimensional problem. And so in fact I'm going to do that. Instead of writing the whole input, which is just the G, the only thing I'm probably going to change is my N and my M. The target where I want to reach. So DE, as I've got it set up here, should be the minimum number of goblins to reach cell NM. Okay, so that's what I'm defining this to be, this minimum value. And now I'm going to use a self-reduction to show how I can relate this problem, the main problem, the minimum number of goblins to reach cell NM, back to other sub-problems, the minimum number of goblins to reach other cells, hopefully. And to do this, I'm going to start with the easiest cell, and this should be this cell here. So I'm going to say if n equals 1 and m equals 1, so I'm in this cell, the number of goblins I need to fight to reach cell 1, 1 is just however many goblins there are in that room, because that's the room I started in. So I just need to fight the goblins in that room, and then I'm done. I've reached that room. Now that I've calculated this room, you'll notice, and let's go back to this bottom room, that to calculate this room, I need to know the room above me and the room to my left. Now, this room was our first one because it had no room above it and it had no room to the left. So it sort of defaulted as our first one we can calculate because we don't need to know any others. Now, luckily, this one and this one, the one to the right and the one below, are both ones we can now calculate. Now that we have calculated this first one, it's G11, we could calculate this one to the right. It's just going to be however many goblins it took to reach the room to the left, plus however many goblins it is that are in this room. Okay. Again, it's however the minimum number of goblins to reach the room to our left, plus however many goblins there are in this room. Okay. And that's again because it doesn't have one above. Likewise, over here, this one has one no to the left, so we can solve this one as well. This discussion allows us to see that we can actually fill in our subproblem matrix going row by row, or by going column by column, or in fact by doing this weird diagonal by diagonal thing, which we usually don't do that unless we have to. Okay. All right, this is actually going to be my base case and my terminating case, and I actually don't need any more. Some of us might be a stickler and say I want a terminating or special case for the first row and column, but I'm gonna wave my hands at it by just allowing my out of bounds calls to do the work for me. So I'm actually going to do my next step here. So this is if n is if n is equal to 1 and m is equal to 1. So now down here we're going to have if n is greater than 1 or m is greater than 1. Okay. Now, if that's the case, I'm going to jump all the way again down to the final problem that we want to solve, NM. And I'm going to go back to that reflection I noticed that the choice I have, and remember in job selection, we tried to figure out what would our self-reduction be based on the choice that we could have. And the choice we could have would be, did I work this day or not? Now in the longest increasing subsequence problem, the choice was, well, which sequence do I add myself to the end of? Which previous sequence do I add this number to the end of? Okay. And then, in this case, the choice is going to be, which room did I come from? To get to the target room, there's only two possible rooms I could have come from, the one above and the one to the left. And so I'm just going to look at those two subproblems and use that to make my decision. So let's see if we can do that here. Now, first of all, we know we're doing the min. So remember, a lot of the times we're going to put these subproblems into a minimizer or a maximizer. Okay. Now what we're going to say is, to reach this room, one thing we know is no matter what, we have to fight the goblins in that room, and I'll get to that in a second. But otherwise, we either fight the minimum number of goblins to reach the room above, or we fight the minimum number of goblins to reach the room to our left. Luckily, here's where we're going to do our recursive bit. We already have a function that expresses the minimum number of goblins to reach a particular cell. So if we want to know the number of goblins to reach this cell, this would be, right, so the room to our left is going to be DE. Remember, this expresses how many goblins will meet there. N minus 1 M. And then the room above us must be DE N M minus 1. We're going to take the minimum of those two. Now that's going to tell us how many goblins it takes to reach either of those rooms. We'll take the minimum, but then we have to say, yes, we're actually going to add on GN GM here. Okay. Now, when I wrote this, I said, what about the first column and the first row? In the first column and the first row, these might not exist. One of these terms might not exist. So I need to do something here to handle that. And often what you can do is I usually make a little comment. I'm going to use the comment sign here just to tell you that it's a comment, but you can either put this before or after your self-reduction. We're going to assume something. I'm going to talk about here OOB, out of bounds. Okay, out of bounds. When we make an out of bounds column, one of these, what do we want it to return? So I'm assuming out of bounds is equal to something. Well, we want it to return something that's not going to mess up my min. Okay, not going to mess up my min. So think about that. You might have had to do that before. What is something that we can put in there that is bigger than anything? Well, infinity. So in this case, we'll say infinity. Okay, that way, if one of these terms does not return is an out of bounds, it's going to return an infinity. The other one's going to return a value, an actual number, and then we take the minimum of those two, and we add GNM on. Now technically, we could try and get this out of bounds stuff to even handle our base case like we saw in the longest increasing subsequence. Maybe we can just get this out of bounds assumption to even handle this. The problem then is if we put infinity in for both of these, we get infinity. And infinity plus something still infinity. So that doesn't work. We'd have to add another additional one that says, and also assume that if the min here is called with 2 out of bounds, it gives us a 0. And that, that's stretching it a little bit further. I find it a little easier to just write this base case down by itself. So we'll do the one terminating case or the one starting off case to be this one here, but then we'll rely on out of bounds calls for the first row and column where we might have one of these two terms missing. All right, the next step then would be to take our self-reduction we've come up with now and try and come up with some code. So again, I'm going to start myself out with just some pseudocode. So I'm just going to call it dungeon for simplicity here. Taking my input, the grid of all the goblins. Now remember, the first step usually is what I call declaration. So I'm going to need something, and I was calling it DE up there. I'm just going to call it D here. Okay. Let D, and we're going to do the same thing here. I'm just going to go 1 to N, 1 to M. Same as above for our G. We have the same dimensions. We had no need to add a 0th row or column. We might have to do that in other cases. Maybe I'll just say here be a 2D array and again, usually I just say the size if it's not already obvious it is, but this will be an N by M. Okay. Then our next step, if this was declaration, our next step is initialization, and initialization always relies on our base case, our terminating case here. So our terminating case here, we'll just go ahead and say, okay, let, what does it say here? It says D11 should be equal to, and we're just copying it straight down, G11. Okay, done. That's the initialization step. Then the remainder is the iterative bit, and it's where we're going to rely on the recursive part of our definition. So since it's the iterative bit, we now need a loop. I'm actually going to go here, and I'm going to comment here. I'm going to go from I equals 1 to N, and J is 1 to N. Okay. Now, in both cases, I'm going from 1 to N, even though we've done 1 before. Now, the reason is we're going to do the whole first row, we're going to do the whole first column, and in fact, we don't want to do the first one over again, but I'm going to just leave that as something that for the implementation worry about. I don't want to have to worry about edge cases like columns and rows and so on in the algorithm. I'll leave that all up to the implementer. So this is what D11 is. In the very first iteration of this, I'm going to skip over the first step because I don't want to do D11 again. But otherwise, we're going to go the whole first row, the whole first column. This should be an M. Okay, but once I've got my iterators set up, and here's where I also say I is an N and J is an M, so that when I start copying this stuff down from above, I know what I'm going to write in. So let's go ahead and do it. I'm going to say, okay, let, what are I calculating? I'm calculating D. It's not an M anymore. It's I, J. Okay. And then what's it equal to? It's this business. So I get to write that all down. So I'm going to get min. And we had two lookups. Now, each of these look like recursive calls here, but remember, in dynamic programming, these are just lookups in the array. And hopefully, we've already calculated those values in the array. So the lookups are D, I minus 1, J. That was my first one here. Again, I in for N, J in for M. Or my second one here, D, I, J minus 1. Again, and then let's be careful, plus we'll take that input list G and add on I, J. Okay, again, being careful not to put N's and M's in here. It should be IJ's. Okay, we got everything we needed out of there, so that means I can move down a little bit and do my end, and then we might think, okay, well, what is it? Where is our value? We want to return some value, and that value should be stored in our bottom right position in NM. Now, it's not always going to be stored there for all of our problems, but for this problem it is. So we'll just return here D, N, M. Okay, so we get to the end here. We return the value in that last location. And I guess the only thing remaining for us to do, well, there's two things. I want to run through a quick example, but I think we should also, step 7 says do some analysis. And hopefully our intuition's getting pretty good here, that what we have here is theta 1 constant amount of work going on up here. This is the stuff that we really need to worry about. This step here, let's just be careful, some arithmetic, a min, some lookups. This is constant amount of work in here, so again, our intuition should be pretty strong here. We get an n times m algorithm, or n squared if they're the same, right? Maybe not too surprising, since there are n times m entries in this matrix that we filled up. So that's probably, again, not too surprising. So again, final comment on that, because we went over it pretty quick here, that actually this, this algorithm, the algorithm analysis for these dynamic programming algorithms is often as straightforward as just looking at our two loops, with hopefully just a quick check to make sure that what we're doing in our loop is actually a constant amount of effort, not itself a loop, a hidden loop. Okay, so in this case, n times m. But let's go ahead and take a look at an example. Now, this is an example here that we looked at on our first slide. We didn't actually solve it, but this is the same example. And I've got it initialized here, where I'm going to be doing my, I've got it initialized with my G11 here. So my red matrix here is going to be, I guess, P. We called it D when we were working it out together. And I've actually added a purple matrix here. Now remember, in our job selection problem, we used the purple matrix to remember which job to select, basically, or which sub-problem satisfied our maximization. We're going to do the same thing here, except what I'm going to store in there are arrows, which is if the minimum room that we came from was the one above us, I will use an up arrow. And if the minimum room was to the left of us, I'll use a left arrow. So in the first room, there was nowhere to come from. We start here, so there's no arrow at all. It's initialized to empty. So we're going to go to the next step here. And in this next step, what we're going to do is we're going to look at our two subproblems. Now remember, on any one, our two subproblems are to the left and above. And since in the row, the first row here, there is no above one, we're merely looking to the left. So here, we're going to be looking to the left one, but not the other one is going to, and remember, we said it's going to return an infinity so that our minimizer doesn't mess up. Our minimizer will just return the one that does exist, in this case 1, and then we add on the number of goblins in that room, 0. So 1 plus 0 is of course 1, and there we go. In my purple matrix, I'm going to remember which room I came from to achieve this number. Okay, remember this is the minimum number of goblins to get here. This tells us how we got here. We came from this room. Of course, that was the only choice for this room, so nothing too special here. Okay, next up. So next up, again, we're going to look at what's the minimum number of goblins to reach this room? 1. Add on to it 3. So 4 goblins, again, remembering to the left. Okay, next up, pretty straightforward. It takes 4 goblins to get here. Add 4 more on, that's 8. It takes 8 goblins to get here now. Again, this path, backtracking from this room will tell us how we got here. Next up, we're going to get 8 plus 1 is 9. Okay, again, backtracking. There was no choice over here. This was the only way we could get to that corner room, was just going that way. All right, next row. This next row, the first one, is like the first row we just did. It has no left entry. So we look above, we get 1 plus the number of goblins here, 2, is 3. And we remember up, of course. All right, next one. Here's sort of our first case that we have that's actually true, where we get both cases not, both of them are within bounds. Okay, so now what do? We finally have to do a min. Min of 1 and 3 is 1. We add on the 2, which is 3, which means it takes 3 goblins to get here, and that's going this route here. Okay, and we can backtrack here and see that. We remembered up. Up was the minimum value, 1 and 3. Up was the minimum, so we go that way. Okay. Next one, 1. And what are we going to look at? We have 2 values, 4 and 3. So we'll take the 3 and we'll add 1, which is 4. That's our left. Remembering left. Okay. Let's continue. Go a little quicker now. 8 and 4. 4 is better. Add 9, we get 13. Okay, 13, remembering left. Because we've got a 13 there, we're probably going to avoid that room in the future, right? Keep that up. Keep that in mind, right? So here's the next point. Let's see. We're then trying to figure out how to get to this room. Should we come from the room that takes 13 to get to, or the one with 9? Probably 9. 9 plus 0 is 9. We remember up. Okay, 3 plus 0 is 3. Remembering up. Oh, here we've got a tie. What does that mean? That means to get to this room that takes 9 goblins, adding 6 on, there's 2 routes we could go. We could go this one, the one I remembered, or I could have had a left here, which means I could have gone this route as well. Now I've chosen to break the tie by remembering up, and that's just a choice we need to make when we make ties. In any algorithm where you have ties, you have to have a choice of how do you break the tie. And I decided up here. I could have decided left, equally good. The only thing you want to do usually when you've decided to break a tie one way is consistently break a tie that way. Usually that's a good idea. So if every time you do it. Unless that leads to some strange performance, in which case you might randomly break your ties. Okay, but in this case I'm going to consistently do it. If there's no reason to otherwise do it consistently, you should do it consistently. So okay, let's keep going. So 4 and 9 looks like 4 minimum. Add on the 5 is 9. Remembering up. 13 and 9. Okay, again we're going to avoid this room again, picking the one to the left. 9 plus 2 is 11. Okay, 9 or 11 looks like we'll pick 9 there. 9 plus 3 is 12. Next row. Okay, 3 plus 3 is 6. Right, we got 7 here, and we've got a minimum of these two is 6, so 13. Remembering to the left. Minimum of 9 and 13. 9 is better. Let's add on 4. That gives us 13 as well. Remembering up. 5 plus the minimum here. 5 plus 11 is 16. Remembering up. The minimum is above 12. Adding on 4 is 16. Remembering up again. Okay, having to remember up. 6 is the only place we could come from. 6 plus 9 is 15. 13 is the minimum. Plus 4 is 17. Remembering up. 13 is the minimum again. Adding 2 now is 15, remembering up. 15 is the minimum of these two. 15 is minimum of 6, add 0 is 15. And it looks like 15 again. So, well, we had 11 goblins guarding the exit. That gives us 26 goblins we need to fight to make it all the way out. And maybe we notice here that if we start in that last room and we backtrack our way out, that's the path that we need to follow to fight the 26 goblins. Okay, you can verify that on the way out. Or, of course, best way to do it is go over here and add up all these numbers. And that should add up to 26. So now we found the optimal route out. Of course, this was a 5x5. We might have been able to brute force that. But imagine doing that on a 100 by 100. This would allow, this algorithm will quite quickly, in 100 by 100, 100 times 100 is 10,000, in about 10,000 steps, allow us to compute the optimal route out of the dungeon. Okay, I think this is all I wanted to say about our dungeon escape problem. Again, it's a toy problem. It's another example of a optimization problem. And so we're going to use this as our sort of blueprint for two-dimensional dynamic programming problems. And I've now got a good handful of them that we're going to look at in the coming videos. Okay, well, thanks for watching, and we'll see you in that next video.